So I'll be talking of an application of non-Archimedean analytic spaces to questions related with the existence of rational points on varieties. So more precisely to local global principles. Now, in order to realize this application, I adapted certain techniques called patching techniques to Berkovich analytic curves. And this, well, made it possible to obtain local global principles. Now, these patching techniques, they are inspired from complex analysis, so from classical complex analytic geometry, but they have found several applications in number theory and arithmetic geometry. So one of them being what we're going to talk about today, the local global principle, and another one being the inverse Galois problem. Okay, so let me start by telling you exactly what this local global principle is that I keep mentioning. To simplify my life, I'm gonna simply use the acronym LGP from now on. This is always gonna mean local global principle. So it all started with the following theorem, which today we know as the Hasse-Minkowski theorem, and which was proven like about a century ago, so in 1921. And it states the following. So it says, if you take Q over the field of rational numbers to be a quadratic form, then this Q is going to be what we call Q isotropic. Now, this means that the equation Q equals 0 has a non-trivial solution. So here, basically over Q. And what the theorem says is Q isotropic if and only if Q is, well, basically isotropic over all of the completions of Q. So it's isotropic over R and over all of the chaotic fields QP. So basically it has, the equation has a solution over Q if and only if it has solutions over R and QP. And this turned out to simplify the problem considerably, because now we have effective over these fields, seeing as they have a better, a richer structure than Q, we have effective methods to give an answer to the question there. So we can do it by computer. Now, seeing as this was very useful, we started becoming interested studying what happens in more general and abstract versions, but of the same sort of principle. So this is what we call a local global principle. We're going to take a field F. So this is played, the role of F is played by Q in the Hasse-Minkowski theorem. We're also going to take these larger fields. Let's denote them by Fi. So we're going to call them overfields, meaning that, well, F is strictly contained in Fi for all I. And, well, we're interested in taking some algebraic variety X defined over F, and we want to study whether X has F rational points. So for that, we study the following principle. So the local global principle states that X has an F rational point if and only if it has rational points over these larger fields Fi. Now, of course, the idea here is that we've chosen the Fi, just like in the Hasse-Minkowski theorem, with a sort of a better structure than that of F, so that studying this side of the equivalence is much easier than studying the starting point. So whether X has F rational points. Now, one very classical version of the local global principle is what I refer to in the title as the Hasse principle, which is basically a local global principle, but where the overfields are completions of F. In fact, they are discrete completions of F. So Fi is a discrete completion of F for all I. So basically this means that we take F, we take a discrete valuation on F always of rank 1, and we take Fi to be the completion of F with respect to this discrete valuation. So now here we see an example of a local global principle which is verified. This is not at all always the case. For instance, nowadays, even by keeping the same choice of field and overfields, like in the Hasse-Minkowski theorem, one can construct counterexamples to the local global principle. In fact, the study of the necessary and sufficient conditions for the local global principle to be satisfied, or even the formulation and the study of the obstructions that stop it from being verified, is a very active area of research. So today we're going to talk about a geometric version of the LGP. LGP, where we're going to be able to use geometric techniques, and F is going to be the function field of some curve. Well, we could have taken something of higher dimension as well, but what we know in that case is very limited right now. So we're going to look at this particular case. Now, this sort of local global principle has had a wave of activity in the past 15 years or so, due to the fact that 3 mathematicians introduced a new approach, a new technique to its study. So the mathematicians are Harbader, Hartmann, and Krashen. And by using a very algebraic version of what I mentioned in the beginning of this patching technique, so they showed in 2009 a geometric LGP, which I'm going to state a bit vaguely. But before that, I'm going to introduce some notation that we're going to use throughout the rest of my talk. So maybe for that, I'll come here. Now let K, from now on, endowed with a norm, denote a complete, non-trivially valued ultrametric field. Let's take over this K the curve over which we'll be working. So C over K. Now this is a reasonably nice curve, meaning it's going to be a projective, normal, irreducible, and it's a curve. We're going to denote by CAN, let's say it's Berkovich Analytic. And by F, the function field of this curve. So this is the curve over which we are going to be working. We're going to study local global principles over the field F. Now, the sort of variety that we're going to study this principle for is a variety that has very strong symmetry properties. So I'm going to write it down and then make a few comments on the hypotheses that we see appearing. So let X defined over F be a projective, homogeneous variety over a linear algebraic group G, which is a rational variety in itself. Okay, so now we're seeing all of these hypotheses pop up. Well, the first one is this homogeneity hypothesis. Well, actually, this one is the one that is the least strange. Because homogeneous varieties are typically ones that we study for which we study local global principles. These are the ones that we understand the principle the best for. So from a historical point of view, this is a very normal hypothesis to encounter here. What it means is that this group G acts on X in a sort of transitive way. So for instance, at the level of geometric points, X is simply going to be a quotient of G, of the group. Okay, so we have this. Another thing that we see appear, and this is, well, a new restriction, one that we would very much like to get rid of, but which seems to be very important, maybe even crucial to make this algebraic patching technique work. So what this means, and we'll see later on when I tell you a bit more about patching, where exactly it comes into play. So what this means is that the variety G is birationally equivalent to some space, to some projective space, P to the power of n, I mean Pn, an n-dimensional projective space over F. So I can give you maybe a concrete example of these sorts of varieties. It's precisely the case of quadratic forms. So if you assume the characteristic of K to be different from 2, and you take Q over this function field F to be a quadratic form, well, then one can take X to be the projective variety determined by Q. I'm just going to denote this as Q equals 0. And we can take G to be the special orthogonal group associated to Q. And then X is going to be a projective homogeneous variety over this group G, which it is a linear algebraic group, which is birationally equivalent to some Pn. Okay, so let's get back. In particular, this means that all of the local global principles that we're going to see apply to quadratic forms if the characteristic is different from 2. So getting back to the statement of LGP with that notation, what they show is that if K is discretely valued, well, then one can construct a family of overfields of our function field F, such that, well, the local global principle is satisfied. So X has an F point if and only if it has Fi points. So I'm not going to tell you exactly what these overfields are. I'm not going to write them down explicitly, but I can tell you that, well, first thing, they are constructed from a certain model of the curve. From a nice model. Of the curve C. And another thing I can tell you is that, well, it's a natural question now. We see that this is a local global principle, but is it a Hasse one? Well, the answer is no. The Fi are not discrete completions of F. In fact, they are not even they are not even completions of F. So LGP HHK, not a Hasse principle. Okay, so what I did was take this algebraic patching technique, adapt it to Berkovich analytic curves. Now that made the technique, it allowed us to have a very geometric point of view on the technique. And among other things, it made it possible to generalize this sort of result of HHK. So here is a preview of this result. I'm going to write it down here. LGP MX for reasons that will become apparent very soon. So what I show is that for the same data as I just introduced 2 minutes ago, X has an F point if and only if X has rational points which are germs of meromorphic functions on the analytic curve CAN. So here, this curly M that we see up here is the sheaf of meromorphic functions. On our analytic curve. Okay, so if we can show that, for instance, the field of global meromorphic functions on our analytic curve CAN is simply this function field F. So if we take into account this and go back to the theorem, we see that it's a very geometric LGP, because it tells us that our variety has a rational point, which is a geometric function on all of the curve, on all of the analytic curve, if and only if on each point of this curve, it has a rational point, which is a germ of a meromorphic function on it. So a first natural question when we see this is, how does it compare to the LGP HHK? Well, we can make a few remarks here. So the first immediate difference is the fact that, well, we don't need this condition on K being discretely valued. So we can show this for any complete non-trivially valued ultrametric field. And then, of course, there is the obvious difference between the families of overfields. But as it turns out, we can interpret these overfields of HHK, these fields Fi, in the language of these of Berkovich curves, and hence show that the LGP MX implies the LGP HHK. And in fact, one can even show that the inverse is true, provided we assume that K is discretely valued. So that the valuation on K is discrete. And thanks to this example, we already see that, well, both of these LGPs, they apply to quadratic forms. Okay, so now, before I tell you a bit more about the consequences one can obtain from the LGP MX, from the fact that it's very geometric and the fact that these fields MX, the overfields, they have quite nice algebraic properties, let me tell you, just take 5 minutes to tell you a bit about this sheaf, how we define it, and maybe recall very briefly the structure of these Berkovich analytic curves. So now the definition of the sheaf of meromorphic functions is actually very natural. We're going to denote the sheaf by curly M. And well, the way we can define it is the following. So in a particular case, if we take Y defined over our complete ultrametric field K as being some, let's say, a normal K affinoid space, so basically this means that, well, we are defining it for the building blocks of our analytic curve. Affinoid spaces, they are building blocks of the Berkovich structure. And we're defining it for normal ones because it's a bit easier and is the only case that we need, since the curve we're working on is also normal. So for these, we can simply define the field of meromorphic functions over this Y to be the fraction field of the ring of analytic functions over Y. And this makes it possible for us to define the sheaf over all of the curve. And in particular, what's going to happen is that for any point of the curve or of this affinoid, the stock, the germs of meromorphic functions on X is just the fraction field of the ring of analytic functions. And now, thanks to the nice properties of this ring, well, one can deduce pretty nice properties on the field too. So for instance, the field MX is, due to the structure of Berkovich curves, it's naturally endowed with a valuation. So it's a valued field, always of rank 1. let's say that during this talk, high rank valuations don't exist. So these are valued fields, but not only are they valued due to the structure of this ring again, they are also Henselian. And this Henselianity property is really crucial when it comes to finding applications of LGPMX, as we'll very soon see. So before I tell you a bit about that, let me also recall very briefly what analytic curves look like by taking the very typical example of the analytic affine line. So before I write down something more concrete, I'll just recall, because it's going to be useful to me later, that this is the set of multiplicative semi-norms on the polynomial ring over K, which extend the norm of K. So these are basically the difference from norms is that here we allow a non-zero kernel. And we can construct plenty of examples which also help us visualize the curve by simply taking an element of K and a non-negative real number. So then one can define semi-norms on the following way. By associating to a polynomial P, which we are going to write in the basis T minus A, the max of the norm of AN times R to the power of N. And well, it turns out that this is an element of the analytic affine line because, well, it's a multiplicative semi-norm, blah, blah, blah. And another property is that if we take R to be 0, well, then we can see that K is actually embedded in this analytic curve, because what happens is that you take A and you send it, let's say, to the semi-norm, which sends a polynomial P on its evaluation at the point A. And one last remark, which is important for the visualization part, is that, well, this point eta AR, actually, it's uniquely determined. It only depends on the closed disk centered at A and of radius R. The closed disk centered at A and of radius R. And this is closed disk. Okay, so there are many other points, but how do these in particular help us see what A1 looks like? So if we start from a point A in K, what we're going to do is associate to it a half line containing all of these points eta AR, so which I defined right here. Now what happens is that R varies from 0 to infinity. We can do the same thing for any other point B of any element of our field K. And let's just take into account this third property, which is that, well, the point eta AR depends only on this closed disk, which means that as soon as B enters a disk with center A, well, then its half line is going to coincide with the one we associated to A. So if we do the same thing, the two half lines eventually coincide. And we can do this for all of the points of K. So we end up obtaining what looks like an infinitely branched tree. And well, like I said, these are not all of the points of the analytic affine line, but they still allow us to see this property that I just mentioned. So this is A1. And since we'll be talking about projective curves, let me just tell you that from here we can construct P1 the usual, very classical way. So by simply adding some infinity point which, when we go back to the tree, is located right here. So we close this half line by taking r equal infinity. And this is not a very complicated point. It's, again, a k point. So the projective line looks like a tree, like an infinitely branched tree. And this is a very useful representation of Berkovich curves because they always have the structure of an infinitely branched graph, so sort of a real graph. But the difference from here being that, well, the graph can contain loops. However, though, at least locally, it's going to look, you can imagine that it looks something like this. So when we talk about these curves, you can picture something like this. Okay, so now let's get back to the LGPMX and see what we can obtain as a consequence of this result. I'm going to keep the statement. So I'll just use the upper half of this part of the blackboard. And the first thing I can tell you in terms of consequences is that, well, it's in terms of quadratic forms. So the LGPMX applies to quadratic forms. And again, thanks to the fact that the fields MX are Henselian, one can show a generalization of the following very concrete result. So it was a theorem initially proven by Parimala and Suresh in 2009, then reproven by HHK by using this algebraic patching technique, and then which I generalized by using patching over Berkovich curves. So what it says is that if we take P different from 2 and Q over QP parenthesis T a quadratic form, then if the dimension of this quadratic form is at least 9, then it's going to be isotropic over QPT. Which I recall means that the quadratic form has a non-trivial 0 over this field. So basically, as soon as it has large enough dimension, we can immediately assure that this is true. And yeah, by the way, if we take equal to 8, then we can construct a counterexample. So this is the optimal bound. Okay, this is in terms of quadratic forms, but then we can say something even in the general case. So we can obtain other local global principles from this one. To see this, let me start by recalling what I believe is a relatively well-known fact on Berkovich non-Archimedean analytic curves, which connects the points of an analytic curve to valuations on the function field f. So I'm gonna erase here now. I maybe shouldn't have erased that, but it's okay. So proposition, and this is fine. So one can construct, let's call this proposition 1. One can construct a bijective correspondence between the points of our Berkovich analytic curve and a certain set of valuations which one can endow the function field f with. So where, let me define it. So V of f is the set of all valuations, non-trivial valuations over f, which, when we restrict to the subfield K, either induce us the starting norm on K, or are trivial there. So there exists this bijection, and I believe that even though the connection is not immediate, this is strongly hinted already when we define the analytic affine line like I just did. So like a set of multiplicative semi-norms. I believe that to be a very strong indication of this. So now we have this bijection, but this is not all. The bijection is such that if, say, to the point x, we've associated the valuation Vx, well then, the valued field, remember this was a valued field, it came naturally endowed with a valuation. So if we complete it, what we're going to obtain is exactly the same thing as taking f and completing it with respect to this corresponding valuation. And now taking this into account, one can prove almost immediately by putting together these few elements that I've introduced, the following LGP. So the LGP states that with the same notation, our variety X has an F point if and only if it has points on all of the completions of F with respect to the valuations in this set. So to see the proof, you just need to put together three elements. So the first one is one I already gave you, is the LGPMX. The second one is, well, this proposition that I wrote down here. So the proposition 1. And the last one, well, it's the fact that the fields MX that we see appearing in the LGPMX, they are Hasselian, which means that we can approximate points. So basically our variety X has an MX point if and only if it has an MX hat point. And once you have all these three elements, you can prove the result quite directly. So now the difference between this LGP and the one that I mentioned before, the LGPMX, is that, well, we have as overfields, so completions of the field F, which might be something that we're more accustomed to seeing. And well, once we see this and we think back to the Hasse principle, which, as I mentioned, is a more classical kind of local global principle, a natural question is whether this is a Hasse principle or whether, well, one can reduce to a Hasse principle starting from this one. Well, unfortunately, this is not a Hasse principle, even if K, our base field, is discretely valued. In fact, there are many more valuations that we see appearing on this set than only the discrete ones. One can nonetheless say something in the direction of the Hasse principle. So let me try and explain what.
Question in the proposition, are you not missing the rigid points?
I am not, because I'm saying it can be trivial. And the rigid points, well, the local ring, the stock of rigid points is a one-dimensional ring, so it's a discrete valuation ring.
I don't see how you get the valuation on the function field of the curve.
Well, it's like over curves. If you take over algebraic curves, if you take the Zariski closed points, they give you a valuation. It's simply because the points are Zariski closed, so the dimension, because of the codimension, the dimension of this ring is going to be 1, so it's a DVR if Kx is rigid. You can take an example. If you take, I don't know, t to be sent to 0, then that's good. That's going to give you as completion K double parenthesis t, which is trivial on K, and which is rigid also. Okay, so yes, I wanted to tell you about this Hasse principle. So this is a conjecture from 2000, dating from 2009. I'm going to call it conjecture A, given by Coyotelén, Parimala, and Suresh. And basically in this language, it states that Well, we can restrict to only the discrete valuations here, but you have to assume already that K is discretely valued. And then one can restrict to discrete valuations on, let's say, the LGP in LGP val. Or in other words, the Hasse principle holds, is true, is verified for our variety X defined over the function field F. So this is what they conjecture. They even conjecture it much more generally than only for homogeneous varieties over rational linear algebraic groups. But let's just keep this terminology. Now, this is a conjecture that seems to be quite difficult. It is to this day known only in some special cases. So it has been shown to be true for, well, quadratic forms. This was proven by, well, the same three mathematicians in the same paper where they announced this conjecture. It's true for classical groups. So when G is classical, given we're working with good characteristic, and this is shown by only Parimala and Suresh in 2020. And very recently, they teamed up and they showed that it's true if G, so our group, is defined over the valuation ring of our field K, so over K0, which is the valuation ring of K. And this was shown by, well, Kolyotelen, Parimala, Suresh, Harbader, Hartman, and Krashen all together. And it's a very recent 2001 preprint. So one can say something using this Berkovich approach. So it's a geometric approach to study the conjecture. We can start by reformulating it already in this language. For K, then I think you can construct counterexample. It's not reasonable to expect that it's going to be true. I mean, if you add other hypotheses, then maybe. But given just like the conjecture is given here, I think you can construct counterexamples. Okay, so yes, let's start by reformulating the conjecture to our language. So let me start by defining a subset as disk, which contains all of the points of our curve such that with respect to the bijection that I mentioned here, the corresponding valuation is discrete. So one can say a certain amount of things about this subset. The first one is that, well, this is a dense subset in our Berkovich analytic curve. And one can describe the points of this curve, be it topologically or algebraically. For instance, one can show that if we go back to this drawing as an infinitely branched tree, well, we know that all of the branching points of the tree are going to be in this set, in the subset as disk. So these are known as the type 2 points. And then we are also going to have some of the extreme points of the tree. So not all of them, but some. And these are going to be some of the type 1 points. So this is now as disk. And the conjecture with this notation can be reformulated as follows. So conjecture, let's call it B. It's equivalent to conjecture A. And it states that the following implication is true. So X has nx points for all of these points in the subset as disk implies that the same is true, but over all of the points of the curve. And then one could conclude by using the LGPM of X that X of F is non-empty. Right, so now we're brought to studying this implication. And what I've managed to show so far is the following. So I'll try to erase here, and hopefully people can read what I just wrote on that part of the blackboard. So I'm going to state a somewhat vague result and then try to explain it semi-heuristically so that you get the idea of how it works. So what we can show is that there exists a model curly C of our curve C and some non-empty subset Z of the special fiber, which is finite and closed, such that if our variety X has a proper model over curly C, which, and this is a real hypothesis that we need to assume for now, which is smooth over Z, well then conjecture B is true. Basically, we have a Hasse Minkowski principle. Okay, so, well, basically the theorem tells us that if our variety satisfies some very strong smoothness hypotheses, then we can show a Hasse principle. Let me tell you a bit about, because, well, we don't get any idea of how we construct the model or what it looks like or how we get to this finite set of Zariski closed points on the special fiber. So let me try and illustrate this by working over a Berkovich curve. Well, the way I do it, it's enough to restrict to rigid and type 2 points. You only need even a finite number of type 2 and rigid points. But in general, as disk also includes some other type 1 points. For now, at least, I get the impression that yes, I think that rigid points and type 2 should be enough. But it's, yeah, it's just what I think, given the proof of the, given a, let's say, an idea of the proof of this theorem. So let's take our curve. Actually, let's take a very, in a certain way, simplified drawing of our curve. I'm going to draw it like this for now. You'll see soon why. This is our curve. And let's take on it something that we call a vertex set. So it's a finite, I'm going to call it V. It's a subset, well, clearly proper, of our analytic curve, which contains only type 2 points. So it only contains branching points and a finite number of them. So the way I drew this, I'm going to assume that that V contains only these 2 points. So the points x1, let's call them, and x2. And to this V, also known as a vertex set, one can associate a, let's say, a model of the curve. So we're going to call it C, curly C, V. Now what happens is that one can construct a morphism, which we call a specialization morphism, a specialization map, which goes from the curve, the analytic curve, to the special fiber of this model that we associated to V. So what the specialization map does is that it induces a bijection between the points of V and the generic points of the special fiber. So here, the points xi are going to be sent on the generic points of these irreducible components. Let's call them eta1 and eta2. So they're the images of x1 and x2. And for instance, what also happens is that this connected component of the complement of V, so which has as boundary points the points x1 and x2, is sent to this double closed point, so contained in both of the irreducible components of the special fiber. And now these are branching points, so they are contained in S disk. Basically, V is a subset of S disk, which means that X of mx is non-empty for all S x in V. So we can construct a neighborhood of this X, which I'm going to call UX, such that X has a MUX point. If we go back to the drawing, so they're going to look something like this. These UX1 and UX2. And what this tells us is that for the conjecture, all of the points that are inside of these two neighborhoods are accounted for. So what remains is to look at the points outside and see whether we can say something in that case. The first thing to remark here is that since the boundaries of UX1 and UX2 are going to be finite, there are only finitely many connected components of the complement of V, which remain outside of the union of these two neighborhoods, so for which we need to account. So let's denote by A1 to AN the connected components of, so the complement of V, which are not entirely contained in the union of the UXs.
Is the reason why you can move from what you have to some open set? This implication with there is some.
This one? Oh, this is a germ, just a germ of a meromorphic function. So yes, it's just the definition of an X since it's germs. And this is just a neighborhood. Good. So we have these AI. It's just when we go back to the drawing, these parts and this one. Let's call this AI, this AJ. So now what happens is that the specialization map pi sends these connected components to Zariski closed points on the special fiber. So for instance, the image of AJ, I told you we're going to denote it by PJ, is pi of AJ, and then it's going to be similar for AI. It's going to be here somewhere. And this is how we get our subset Z. So the one that we see here in the statement. This is our subset Z. And now we can construct a criterion of when our variety has rational points over these connected components. So statement. Now, if X has a proper smooth model over O0 of AI, this being the ring of analytic functions on AI, which are bounded by 1. So basically all of the elements in O of AI, which are always smaller or equal to 1. This ring is actually considerably smaller than the one of all analytic functions. So if our variety has a proper smooth model over this ring, well, then we can show that it has a point over the field of meromorphic functions over AI. And if we do this for all I, then since these are the only points that were unaccounted for, one can conclude that the conjecture B is true, or basically that this theorem that I wrote here is true. Yeah. And one last, yes? So Z depends on X. Z and the model depend on X. Both of them depend on X. So one can show this. And how does one connect this to smoothness over the Z? Well, it's by a result of Bush. So Bush, I'm swiping some things under the rug. You need to be a bit careful about the model, but like I said, this is semi-heuristic. So O0 of AI can be shown to be this is the completion of the corresponding local ring of the image of AI with respect to pi, so of pi. And the proof is basically a consequence of the fact that this ring has pretty nice properties, such as, for instance, being a complete regular local ring of dimension 2. So one remark here, before we continue with something else, is that, well, I gave this statement, but one needs to be careful because this, if there were to exist some bad reduction point of X on these AI, then this is never possible. But this is not a problem. So if I'm going to erase this, yes?
There's still something which is not clear. So at the starting point, how would you choose this pair X1, X2?
I just took any vertex set. For now, this you can take any, but then you need to refine. I'm about to show a little bit how you would need to refine.
If they are too far apart, you collapse everything. Right?
I mean, you can add as many as you want to. Yes.
No, this way.
This is fine.
It should keep the cycle. I think. I mean, you didn't define what the vertex.
No, I did not define what a vertex set is. No.
If you take those points too far away, you collapse all the structures.
Yes, but you can show that you can always take them quite nicely.
Oh, okay.
Meaning to something that, yeah, something that resembles to what I drew. Okay, I'll just tell you why this is not a problem, what I just said. So a remark, this statement is not possible if one could find some point, let's call it Z, in, let's say, one of the AI. So this is a rigid point over which our variety has bad reduction. So if the Z, for instance, it exists somewhere, let's say, I don't know, here, or maybe here, since I have more place. But this is not a problem because we can just refine a bit what I constructed here and get rid of this problem. So not a problem because, well, Z, as it is a rigid point, it's an element of S disk. So one can show that X, one can find a neighborhood of Z, just like we did for the points of V, UZ, such that X of M UZ is non-empty. So if we go back to the drawing, we can also assume this UZ to be strict, meaning that its boundary points are always branching points. So this is going to be somewhere here. And now all that we have to do is replace V by taking V and adding to it these boundary points. So this is a new red point, and we'll replace V with V1, which contains at the same time V and the boundary points of UZ. And now we've gotten rid of Z because we only need to take a look at this part. And in terms of the model, because that, of course, is going to change the model as well, what's gonna happen is that we're gonna add another irreducible component. So now the generic point is eta 3. And the drawing, basically, the way we constructed X3 tells us that we don't need to worry about the points of this irreducible component, except for the double point here. That's the only one that interests us. And okay, I think I'll stop because the time is up. But yeah, as a last remark, maybe one can, from this way of approaching things, prove that the conjecture is true for quadratic forms. So it's not a direct result. You have to combine it with the theorem of Springer. But conjecture B is true for quadratic forms, a result that had already been shown by Coyotelén, Parimal, and Suresh. And yeah, of course, provided the residual characteristic K is different from 2. Okay, and now I'll really stop.